Now we will consider the wideband FM. Now wideband FM, to calculate wideband FM, first we will consider the exponential notation. So C can be written as A e to the power j omega ct plus mf sine omega m t. So A e to the power j omega ct plus e to the power j mf sine omega m t. Now the second term is a periodic function of with omega m as frequency, angular frequency. So we can write e to the power j mf sine omega mt. We can write it in terms of Fourier series Cn e to the power jn omega mt for 1 by minus twice fn to 1 by twice fn, and the coefficient Cn equal to fm minus pi by omega m to pi by omega m e to the power j mf sine omega mt into to the power minus jn omega m t dt. Now putting x equal to omega m t, we can write Cn equal to 1 by 2 pi minus pi to plus pi e to the power j mf sin x minus x dx nx, sin x minus nx into dx. So this one is actually the nth order Bessel function. Jn mf. So if we plot, Bessel function is a special function, so its value is dependent on order and this mf argument. So if we plot mf, we can write, or sorry, we can draw. This one is for J0 mf, this is 2.4 nearly, and all the other will start from 0. So this one is J1 mf, this one is J2 mf, and so on. So all the J1, J2, J3, J4 all will start from 0 except J0. So we can write C that means the carrier that can be written as A n equal to minus infinity to plus infinity Jn mf e to the power j omega c plus n omega m t. So st can be written as A summation n equal to minus infinity to plus infinity Jn mf cos omega ct plus n omega m t. So this is the expression for the wideband FM. It depends on this Bessel function. Now as you can see that this summation limit is from minus infinity to plus infinity. So theoretically its bandwidth is infinite. This bandwidth is theoretical bandwidth, not practical. Theoretical bandwidth is infinite, as this series is infinite series. Now, few properties that we will use. Important properties. One is Jn mf equal to J minus n mf for even n, and Jn mf equal to minus J minus n mf for odd n. For small mf, J0 mf is nearly equal to 1, and this one is 1. J1 mf is nearly equal to mf by 2, and Jn mf nearly equal to 0 for n greater than 0. So using this property we can verify for narrowband FM when mf is small, the corresponding expression from this we can write St for narrowband FM is nearly equal to, first we have a Jn mf. First we have to calculate n equal to 0 is nearly equal to 1. So a into cos omega c t, n equal to 0, omega c t, plus mf into a mf by 2, j1 equal to mf by 2 into cos of omega c plus omega m t, and for the second term minus 1, it is, we have a negative sign, minus mfa by 2 cos of omega c minus omega m t. That means we are getting the same expression that we have discussed earlier for narrowband FM. So theoretically the bandwidth of FM is infinite. So if we try to draw with increasing this is for mf less than 1, this is narrowband FM. So if we increase the value of mf, what will happen? More and more number of Bessel function will come. So if mf is larger, then J1 will appear, J1 was there, J2 will appear, then J3 will appear. And second thing is that J0 is decreasing in this way. So more the value of MF, we will get lesser amount of carrier and some more number of sidebands, say MF of the order of 1 or greater than 1 rather. Now if MF equal to 2.4, this is a special case, MF equal to 2.4, under this condition J0 is 0, so there will be no carrier and more sidebands will be there. Note one thing, that the sideband amplitudes are not identical. They are actually depending on this, they are dependent on this variation, they are not constant, so they will vary. This is a special case. Now if we increase it further, then again J0 will appear. That means for further larger MF greater than 2.4, so carrier will reappear and more sidebands will be there, something like this. And more sideband means more bandwidth. So in this case this is the bandwidth, for this case this is the bandwidth, for this case this is the bandwidth, for this case this is the bandwidth. So what we are getting is more the value of MF, more will be the sidebands and larger will be the bandwidth. So bandwidth is actually dependent on the value of modulation index. And for commercial FM or practical purpose FM, we use wideband FM, and the value of modulation index is always kept greater than 1, unlike AM. For AM modulation index is less than 1, for this case modulation index is greater than 1. For all practical purpose, we have to determine the bandwidth of this wideband FM. So theoretical bandwidth is though infinite, but for practical purpose we have to limit the bandwidth, and for that we can use CARSON'S rule, and according, it is coming from experimental observation. So according to this rule, we can calculate the bandwidth of FM, that is equal to 2 into delta F plus FM, where delta F is the frequency deviation and FM is the maximum frequency component of the modulating signal or baseband signal. That can also be written as 2 into 1 plus MF into FM. So for practical purpose we use CARSON'S rule to determine the bandwidth of a wideband FM. Now we will consider the modulation and demodulation part. For narrowband FM, generation, the expression for narrowband FM is this, that we have already discussed: 2 pi fct minus mfa sine 2 pi fct sine 2 pi fm t, and this expression is used to design the modulator. So here we have the baseband signal, this sine wave was coming from the because of presence of integrator. So we need an integrator. We will get this one, that must be multiplied with sine 2 pi fct, and from where sine 2 pi fct will come? It will come from cos 2 pi fct. So we must have an oscillator that will generate cos 2 pi fct, and that is passed through a 90-degree phase shift, 90-degree phase shifter to produce sine 2 pi fct. They must be multiplied using a product modulator. They are multiplied with a product modulator. So this is one part, this one, and we need this one. So oscillator we have subtractor actually, so we can write it in this way. And here we have the plus sign, and here we have the negative sign. Output is narrow band FM. So this is the generation of narrow band FM. Now the generation of wideband FM. We have two methods. One is direct, another is indirect. These are two methods. We will discuss only the indirect method, because direct method we use a VCO, or you can use some PLL type of circuit. But indirect method, what we do first, the only indirect method that we are going to discuss is the Armstrong method. In this Armstrong method, first we will generate a narrowband FM, and from that narrowband FM we generate a wideband FM. So baseband, then we have an integrator, next we have narrowband phase modulator, narrowband phase modulator from a crystal oscillator, we generate the corresponding carrier signal. So this is the simplest form. Actually Armstrong method is little bit complicated, but we are trying to understand the simplest form. Then this narrowband FM, this one is narrowband FM. That narrowband FM has to be converted into wideband FM, and for that we have frequency multiplier. And we will get wideband FM. This is what we call the Armstrong method of generation of wideband FM. Now we are going to discuss the FM demodulation. Like AM, FM may be demodulated with synchronous fashion or asynchronous fashion. FM synchronous detector means PLL. That means the PLL may be used as FM demodulator. But in this demodulation part, we will discuss out of number of FM demodulators. We will try to understand just one type of FM demodulator which is asynchronous in nature, and that is the slope detection. Simple slope detector. The basic principle of operation of slope detector is like this. First of all, the FM signal must be converted into equivalent amplitude variation. So frequency variation must be converted into equivalent amplitude variation. Then once we get amplitude variation, we can use envelope detector to demodulate that AM signal, and we should get the demodulated output. So this is the basic principle of operation of this simple slope detector. So let us try to understand the circuit. So this section is the envelope detector, and this part is used to convert this FM into AM. Output voltage of tank circuit means this one can be drawn in this way: frequency versus voltage variation. This one is tuned at frequency Fc, this one is tuned at a frequency of Fc plus delta F. So this one is Fc and this one is Fc plus delta F. So if the frequency lies between Fc to Fc plus delta F, the output voltage of this tank circuit here, say if the frequency is increased from Fc to Fc plus delta F, then the output voltage will be increased from V1 to V2 in a linear fashion. That means the frequency modulation will be converted into equivalent amplitude modulation. So once we get amplitude modulation, that amplitude modulated signal may be demodulated with the help of this envelope detector. So this is the basic principle of operation, but there are certain disadvantages. As you can see that we are only using one part of the total frequency deviation, like Fc to Fc plus delta F, but we cannot use Fc to Fc minus delta F. This region is cannot be used for this particular circuitry. Second one is inefficient. So if we write the disadvantages, this one is inefficient. Second, we are assuming this section is linear, but actually this is not linear, because this is a tank circuit, so it will follow some curved path. So it shows linear characteristics over a small frequency range. And last point is adjustment is not easy, because we have to adjust two tank circuits. One is at FC, another is FC plus delta F. So we have two things to operate. So that makes it its adjustment becomes clumsy. But only advantage is that the circuit is very simple. It is very easy to understand and it is very simple. Well, there are some certain other type of circuits available, like double slope detector, then Foster-Seeley discriminator, ratio detector, etc. But we don't want to go to that details of those circuits. What I want to tell you is the basic principle of operation. Principle of operation is same in all the cases, but thing is that if we want to reduce these problems, we have to make the circuit little bit complicated. So those complicated circuits are there, but right now we are not going to discuss all those things. This simple kind of slope detector is also called frequency discriminator circuit. This is also called frequency discriminator. So we are finishing our FM part with this circuit, and we are not going to discuss the other circuits.